For my physics teachable moment project, I'm going to be going over mirrors and lenses and identifying all the unique characteristics about each of those. So for object distance, we're going to use the variable SO. So object distance is going to be the distance that we're going to have an object away from a mirror or a lens. For image distance, this is going to be the same thing. The distance the image, which it appeared at, is from the mirror. One thing to keep in mind about images are formed on the point where rays actually intersect or appear to originate. Moving on, our next thing is lateral magnification. So this is going to stand for M for our magnification, and it's going to equal this formula right here. So it's going to equal negative SI over SO, and this also equals H prime over H. As we just learned, SI is image distance and SO is object distance. Magnification is the relationship, or is the quotient, is the division between SI over SO. Notice that it's a negative value, so if the image is a farther distance away than the object, we know it's greater than 1, that means the magnification is going to be greater, and vice versa. We can also use this to figure out for our H prime value and our H. So our H prime value is the reflected height, which is going to be associated with the image, and our regular H value is going to be associated with the object. Moving on, we have a real image, and the definition of a real image is where light actually passes through the image point. For a real image, an example of this could be where the light rays can be displayed on like a screen, for example. And in a real image, this is where all the light rays are converging at one point. For a virtual image, this is where the light doesn't go through that image point. So going back to our example of the screen, a virtual image does not appear on that screen. This is where the light rays actually diverge from each other instead of converging like a real image. Okay, so I drew down a basic flat mirror. In this diagram, you can see that the distance that the object is away from the mirror is the same the distance the image is from the mirror. So these are the basic properties of a flat mirror. We will notice that the object distance, image distance is the same. The height of the object and the reflected image are the same. So this will tell us that the magnification is equal to 1. So that formula we just talked about, M equals negative SI over SO equals H prime over H. We know SO and SI equal each other, and H prime equal each other. This means that the ratio between them is the same. This will equal 1. Now, the reason this negative gets canceled out is because the SI is on the virtual side. When we look at a flat mirror, the side that the object is on, we're going to call the real side. And the side where the image is, we're going to call this the virtual side. And this is something to keep in mind when describing the characteristics about an image formed from a mirror. Okay, so I drew below a concave and convex mirror. On the left, we have our concave mirror. Now, this is the shape of what a concave mirror looks like, and this is different from a flat mirror that we analyzed before, we looked at just before. So, if we can imagine a concave mirror extends out to a sphere, just like so, the center point would be right here. This is the center of the mirror. Now, the distance between the center and the mirror is the radius. When we have parallel beams of light rays that are coming from this distance that hit the mirror, they're all going to reflect off the mirror and converge at one point. This point we call the focal point. Now, the focal point, neatly, is just half the distance of the radius. So in a problem, if we're given the radius of the mirror, we can figure out what the focal point is, where the focal point is. For our convex mirror, that'd be the same case. We can envision this as a circle that goes all the way around. Our center point would be here. This distance is the radius, and our focal point would just be half of that. Now, two big things that we need to take away from a concave and convex mirror are two properties that are true about them. The focal point of a concave mirror is always positive. That is just a fact. And for a convex mirror, the focal point is always negative. Now, these are very handy tips to know when we're analyzing problems, and will really help us figure out the object distance and the image distance. So, introducing those ideas, we have this equation called the mirror equation. The mirror equation allows us to see that relationship between the focal point, the image distance, and the object distance. This equation states that the inverse of a focal point is equal to the sum of the inverse of the object distance and the image distance. So, if we go back to our concave mirror and we envision an object right here, we can agree that this object is on the left of this mirror. Knowing that, we say that this object is in front of the mirror. If it was behind, we use the terminology behind the mirror, on the back side. Same thing for a convex mirror. On the left, if there's an object there, we say the front. If it's on the right side of the mirror, we call it the back. One last thing that we could take away from this is that, I should go back to the front and back. The front side, where the object is the real side, and the back side will be the virtual side. Same thing for a convex mirror. So whatever side the object is on, and they say it's the front side, that is the real side. For a concave mirror, most of the time the image is going to be formed on the real side. And for a convex mirror, the image will be most of the time formed on the virtual side. So I will write it down. This is the real side. This is the virtual. And same thing for a convex mirror. This is the real side, and this is the virtual side. So, new things that we've been introduced is the mirror equation. Oh my goodness gracious, I misspelled this. That's supposed to be this. Mirror's equation. We also learned about that for a concave, the focal point is positive, and the focal point for a convex mirror is negative. We also learned that the front side is the real side, and the back side is the virtual side. So, with that information moving on, we're going to move on to our next part of the unit, and we're going to actually draw some ray diagrams to fully understand this concept. Okay, so below I wrote down why we use ray diagrams. So the first reason is we use them to determine the position and size of an image. This is just a quick way to check if the image is going to be bigger, smaller, if it's inverted or upright, and if it's on the real or virtual side. Now, the other point we use is that if it's a graphical construction which tells the overall nature of the image. As I just said, it's going to tell us those characteristics about those image. And one more thing, they can be used to check the parameters calculated from the mirror and magnification equation. So if we're doing a problem and if we do a quick calculation and see if the image is bigger, we could do a ray diagram to ensure that, to back up that we did the math right, and vice versa. So below I drew the three rays that we draw in a ray diagram. So the first one is going to be drawn parallel to the principal axis and is reflected back through the focal point. The second one is drawn through the focal point and is reflected parallel to the principal axis. And then the third one is drawn through the center and is reflected back upon itself. Now, using what we learned about ray diagrams, we're going to do a couple example ray diagrams to see how we can use this quick trick to figure out what the image is going to be from a certain mirror. Okay, so below I drew a concave mirror, and the object distance is going to be greater than the radius. So we know the center is going to be the same distance as the radius. So as we learned on the previous slide, what I wrote down, is that we have three ray diagrams that we got to draw. So the first one is going to be drawn parallel to the principal axis and reflected back through the focal point. So we're going to do that. So we're going to go parallel to the principal axis, hits the mirror, and hold on. Focal point is half right here. It's going to be reflected back through this point, and it's going to continue this direction. Okay. Our second one is going to be drawn through the focal point and then parallel to the principal axis. So I'm going to try my best. Here, through the focal point, and then it's going to be reflected parallel to the axis. So that's our second ray diagram. And then our last one is going to go center to center. So here's center, and then it's going to bounce back upon itself like that. So now we see where the general area is where they all intersect, which is roughly around here. So we know our image is like that. So when we do a ray diagram, there is 4 things that we have to analyze about this image. First thing we realize is that the image is going to be real. It's real because it's on the same side as the object. The second thing is it's going to be inverted. The third thing is that we can notice that it is smaller. It's small. It looks smaller than our original object. And you can just do that off base of judgment. And our fourth thing that we can analyze is where the image is formed. So we can see it's between the focal point and center. So between focal and center. So these are the 4 things we look at when we're doing a ray diagram. So let me erase this and we're going to do another one. So I drew a convex mirror and we're going to do the ray diagram for this one. So instead of doing 3, I'm actually going to do 2 because it's a little bit more difficult to do that second one, which is focal point to parallel axis. So I'm going to do parallel, and then it's going to go perpendicular. Then we're going to do the reflected to focal point, and then I'm just going to do center to the center. That's it. So this intersection right here is enough to give us our image. And from this image, we can figure out that it is upright. We know it's virtual because it's on the opposite side of the object. We know it's smaller magnification. And we can tell the location of it. It's going to be before that focal point. So that is another ray diagram. Hopefully it helps you get the idea of how ray diagrams could quickly help us understand what the image is going to be formed from an object on a convex mirror from a certain distance away. So the next part of this video is going to be discussing lenses. In lenses, we have 2 types of lenses. We have converging lenses and diverging. In converging lenses, the light rays that are coming from the left are going to enter the lens, and when they go through the lens, they're all going to reflect and come together at one point. This is where they're going to be converging together, creating the focal point. For a diverging lens is basically where the thickness is the smallest at the center, where a converging lens, the thickness at the middle is the thickest. The rays that are going to be coming in are going to diverge and actually go out in this direction. So there's no focal point that's going to be formed on the right side, but the focal point instead will be reflected upon where the side where the rays came. So this leads us to understanding that the real and virtual side is actually going to be swapped for lenses as compared to mirrors. So for the real side, before it was on the left side, the real side is actually going to be on the right. This will be the real side. And the virtual side will be the side where the rays are coming from. So that is our biggest and newest idea with lenses. For a converging and diverging lenses, the virtual and real sides are flopped. One more note I would like to add is at the focal points. So this is where the rays are all going to be intersecting. For a converging lens, this focal length is going to be positive, and the focal length for this diverging lens is going to be negative. So again, the 2 main takeaways from this is that the converging and diverging lenses, the virtual and real sides are swapped, and that the focal point for a converging lens is positive, and the focal point for a diverging lens is negative. Okay, so I wrote down the lens maker equation. The equation is, as you can see right here, 1 over f equals the index of refraction minus 1 times 1 over the radius 1 minus 1 over radius 2. So the focal length of the lens is related to the curvature of its front and back surfaces and the index of refraction of the material. I drew down our a converging and a diverging lens. So the main difference between these lenses and mirrors that we went over previous is that there's a thickness in this converging and diverging lens, and we have to take into account for this thickness. So this is the equation we'll be using, taking account of the radius of the curvature of the two spheres that are joined right here that make this sort of lens. Now, this is how you get the actual precise focal point. But for the equations we're going to be doing for practice and the ones that we've done in class, we're going to ignore the fact that there is some sort of thickness. This will lead the answer to be a little incorrect, but it's fine because we're just going to go briefly over the concepts of the ray diagrams with lenses in this next part. Okay, below I drew a ray diagram for a lens, and this lens is a converging lens. In this ray diagram, the object is going to be placed farther than the focal length. So we know the focal length for a converging lens is going to be on the real side, which is the right side of the converging lens. But we also, just for measurement purposes, can do the same distance on the virtual side, the false focus. So when we're going to do this ray diagram, the first one's still the same rules. We're going to go parallel to the principal axis, and then it's going to go to the focal point and draw it this way. Our second one we could do is from center. So I'm going to try my best to go to the center point right here. The center, it meets over there. And then our last one is going to be false focus. And then once it hits the lens, it's going to be straight. So they intersect in this area, so we know that our image is going to form there. Seeing this, we can right away tell, without doing any math, that this image is a real image. And we know that it's inverted. We also know that it's going to be past the focal point, or I should say focal length. And then if we want to figure out if it's larger or smaller, we could just use the magnification equation. M equals negative SI SO. So we use that equation to figure out if it got bigger or larger. Sorry, bigger or smaller, yes. Okay, so I drew down a converging lens, and this the object is going to be placed between the focal point and then the lens itself. So the first one we're going to do, it's going to go parallel, and then once it hits the mirror, it's going to go to the focal point. The second one is going to go to the center of the lens, so right here, and then all the way through. And then the third one is going to go, I drew this a little funky, but it's supposed to be going from the false focus. So let me do the dotted lines here to the lens and then go straight. So now none of these rays are actually converging, so we know it's not going to be a real image. It's actually going to be on the virtual side. So if we do the ray diagrams, but we're going to do the dotted direction and the opposite direction, we see for this ray right here, it's going to go up. And then we know the other ray is going to be this top ray right here, which is going to go back like so. And we know that they're going to intersect right here, so we know the image is formed right here. This image is going to be a virtual image, and we can tell it's upright. And we know it's going to be past that focal length. And again, if we want to figure out if it's bigger or smaller, well, this one looks bigger. We could just double check it using the magnification equation. All right, let's do one more after this. Okay, in this lens, for our diverging lens, I put the object farther than the focal length. So again, we're going to do our 3 rays and figure out where this image is formed. So the first ray is going to be parallel to the principal axis. And because this is a diverging lens, it's going to go off in this direction, because it's going to, this lens right here, it's going to go in this direction, as you can see. Our second one is going to go to the center, like so, all the way through. And then our third one, it's going to go in the direction of our focal point right here. So we're going to try our best to eyeball it. And this should go all the way this way, but we're not. We're going to draw it then parallel to the principal axis, because that's our false focus to parallel axis. Now, again, this is a diverging lens, so none of the lenses, this is a divergent lens, so the rays are not going to be converging, so we're not going to have a focal point where an image will form, so we're going to have to go the opposite direction of these rays to see where it forms. So if we look at this one right here, it's going to go back in this direction. Sorry, I should hit that focal point, just like so. And then this other one right here, and then you can see these two rays hit each other. So right now our image is formed right there. And right away we can tell by this image is it's virtual, because it's not where the real light rays are intersecting, it's the reflected rays, the rays that we have to dot it back to, and we can tell it's upright. Location, it's in front of the focal length. We can be a little more specific about that if in more words. It's closer, it's between the focal length and the mirror, sorry, the lens. And then our last one is magnification. It looks smaller, but again, we can use this equation to ensure that we did the ray diagram correct. Okay, hopefully that helped. Now we're gonna move on to the last part of this video, and it's gonna do some word problems. Okay, so I wanna end the video with doing a couple of word problems and equations. So this first one is going to be a convex mirror with a focal length of negative 20 centimeters. So we're going to write that down. Our focal point is negative 20. Forms an image. So we know our image distance is 15 centimeters behind the surface. So this is going to be negative 15. If the object has a height of 1.2 centimeters, what is the image height? So image height, if you remember from earlier, is our h prime value. So if we want to figure out what our h prime value is, we can use the lateral magnification equation. So we are looking for our image height, which is h prime. We have the h value and we have the image distance. So we have to solve for our object distance to figure out what our h prime distance is. So using the mirror's equation, we can solve for what the object distance is. So it's going to be 1 over negative 20 equals 1 over 20 plus 1 over negative 15. If I put this in my calculator, it comes out to be 60 centimeters. So once we have this number, we could plug it into this equation over here. So we know negative SI, which is going to be negative 15 over 60 equals h prime over 1.2. A negative times a negative is 15, and we're going to cross multiply. So 15 times 1.2 is going to be 18, and it's going to equal h prime times 60, divided by 60, and we know h prime is going to equal 0.30 centimeters. So this is how we're going to solve a problem that's asking for the image height. So here's our second question. If an object is placed 12 centimeters from a concave mirror, and it produces a real image 8 centimeters from the mirror, that's a statement. And the second part is asking the object is then moved to 18 centimeters. Where is the new image distance? So first thing I would like to note is our object distance for the first part is going to be 12 centimeters. And this is a concave mirror, and it produces a real image 8 centimeters. So the image distance is going to be 8 centimeters. And just for a quick visualization, this is going to be a concave mirror. It's 12 centimeters from a concave mirror, so it's going to be at 12, which represents our object distance. And then it's going to produce a real image, so it's going to be on the real side of concave mirror, which is going to be the left side. So this is where our image is going to be. So just a quick visualization. So we can use our mirror's equation to solve for our focal length, which would be 4.8 centimeters. Now that we solve for the focal length of this mirror, the focal length is it's the same for each mirror, so it doesn't depend on where the object is. So if we move the object, so the object is moving at 18 centimeters, the focal length is not going to change. So we use the mirror's equation again, and we plug in our values, so this can be 1 over 4.8 equals to our object distance 1 over 18. We could solve for this new image distance because the focal point, the focal distance from the mirror is not going to change at all. So I plug this in my calculator, and this is going to come out as our image distance equals 6.545 centimeters. So this is how we solve this type of problem. The biggest takeaway is that our focal length does not change. It is the same for the mirror because the focal length is radius divided by 2, and if the mirror does not change, the focal length does not change. Okay, let's do one more and we'll be done with this video. Okay, for this question, it's asking if So this question is asking, an object is 12 centimeters from the surface of a spherical Christmas tree ornament that is 8 centimeters in diameter. What is the magnification of the image? So first takeaway is the object is 12 centimeters away from the surface of the spherical Christmas tree ornament. So we know the object distance can be 12 centimeters. The other thing I would like to know is the surface of a spherical Christmas tree ornament. So this is the description of what a converging lens looks like. I'm not going to be using a diverging lens because this is not your typical shape for an ornament. So if you have any questions on what the lens is going to be like, you can clarify that one, who made the question. So moving on, we know it's a spherical Christmas tree ornament that is 8 centimeters in diameter. So if we know the diameter is 8 centimeters, we know half of the diameter is the radius. So the radius is 4 centimeters. And if we remember our focal length equation, focal length is half the radius. So that'd be 4 divided by 2, which is going to leave with our focal length of 2 centimeters. Now go back to our converging lens. We know the focal point for a converging lens is positive. So if we go to our magnification equation, m equals negative SI over SO, we have the object distance, so we have to solve for the image distance. So this is why we're going to use our mirror's equation. 1 over f, which I'm going to plug in as 1 over 2, equals our object distance, which is going to be 1 over 12, plus 1 over our image distance, which we're solving for. Now, make sure 1 over 12, this is actually going to be a negative value. And the reason is because the object and where the image is, the image is going to be formed. Let me redo that one. So the focal point is going to be on the positive side, which is going to be over here. But the object for a converging lens is going to be on the left side. Because the two are on opposite sides of the lens, we know they have to have opposite signs. If the focal length is positive, that means the object distance has to be negative. Okay, moving on, we use the mirror's equation to get our image distance, which we're going to get our image distance, which is going to turn out to be 1.714 centimeters. Now, we use our magnification equation, so this is going to be negative 1.714 divided by our object distance, which is 12, and this is going to come out to be positive, because remember this is a negative value, positive 0.143, and that's our magnification of the image. So for this question, just a quick review. Converging lens, the focal point is a positive value. Our object is going to be from the surface of the spherical image, which is going to be the opposite side of our focal point for a converging lens, which is going to be the left side. So it's going to be a negative distance. Our magnification equation is right here. We have a negative over a negative, so that's why we have a positive value. Make sure when you write this down, you make sure you denote if it's positive or negative. You have to write that down. All right, thank you for watching. I hope you enjoy this video and that you learned something new about mirrors and lenses. All right, thank you and bye.